Go ahead and share my slides on here. All right. So thanks for having me. I'm super excited to talk about planet formation and to discuss some of the questions and answers that we've come up with over the years about how planets are forming. Here we go. So I think planet formation is really interesting because planets are sort of unique in that they're the astronomical object that are sort of closest to home for us, right? So we live on a planet, and so if we want to know what happened before in the history of the Earth, or if we want to know where we're going, planet formation can help really help us understand a lot of those things. Outside of the Earth, of course, it's also super useful. So understanding planet formation can help us understand the history of the solar system. It can help us understand the history of other solar systems. And it'll also help us answer really important questions like the origins of life. We think that a lot of these things start on planets. And so if we can really understand what happens to a planet during its formation, that'll affect what it looks like on the surface, then we can really start digging into this question of life and the origins of life in our universe. So part of my personal interest in planets is that I think they're a really unique object. So compared to other astronomical objects like stars or galaxies or clusters, planets are super small, but they are really complex. So they live in these solar systems, they interact with other planets, they interact with their host stars. They've got lots of interesting science going on the surfaces. And so I think for that reason, planets are really exciting, even though they are small in astronomy scales. So I wanted to start just by talking about some of the ways that we start to learn about planets. So as I mentioned, we interact with planets on a few different scales. So our data reflects that. We have data about planets on lots of different scales. So for example, one thing we can definitely do is we can look at the planets in our solar system. So the Earth, Moon, Mars are all kind of nearby. This is a graphic from National Geographic that just shows recently all of the different missions that have been had to places in our solar system. So, we've checked out the sun, we've checked out a lot of the terrestrial planets, the moon many, many times. But we also learned a lot about the outer solar system. So going to planets like Jupiter, Saturn, beyond, and also looking at some of the smaller bodies in our solar system. So the moons of these giant planets, looking at the asteroids and comets that are farther out in our solar system. So for these, obviously, we can do some firsthand investigation into planets and the history of these planets by going ourselves or by sending a rover or a satellite to take pictures or samples and bringing them back. So that's sort of one level of data that we can get on planets by going out and looking at them firsthand. The other things that we can do within our solar system, though, is just by sort of looking at the whole solar system all together and seeing what sort of patterns we can learn about. So we can learn about what the planets are made of. We can think about how the orbits are spaced out, how big the planets are, how far away they are from each other. Those sorts of things can also help us learn a lot about planet formation, and we'll talk a little bit about those today. And then finally, for a kind of overarching big picture of what planet formation results in, we can turn to exoplanets, or any planet that's outside of our solar system. So if we look for a bunch of exoplanets and we start to measure their properties, we can just check that, we can check how our solar system fits into these other exoplanet systems. And we can also check that when we come up with theories of planet formation, they work for our solar system, but they also work for this huge population of exoplanets. So our data comes from lots of different locations. And so I thought what we could do today is to talk about planet formation in the context of 4 sort of main pieces of evidence, or 4 clues, if you'd like. So the 4 clues we'll talk about, the first one is just the structure of the solar system and what we can learn from that. We'll talk a little bit about images of protoplanetary disks. So protoplanetary disks are, there's a sort of artist rendition over here on the right, but these protoplanetary disks are when we have a star and a kind of mess of gas and dust around it, but that gas and dust hasn't quite yet coalesced into planets. So it's sort of the step right before we actually get our planetary system. We'll talk about exoplanet populations and how we can use those to figure out a little bit about planet formation and what exactly needs to be happening at various steps. And then finally, for the kind of icing on the cake of planet formation, we'll zoom in on the Earth and think about some of the features on the Earth that we also need to be able to explain to kind of finish up our story of how planets are forming. So these are 4 clues for today, and I'll just go ahead and jump into this first one. So starting with our solar system structure, you're all probably super familiar with these kinds of diagrams, this solar system, but we know we have our sun in the center. Most of the solar system's mass is in the sun. Our planets are, super kind of insignificant compared to the mass of the sun. Outside of the sun, we have some small rocky planets that are close. So this is Mercury, Venus, Earth, Mars, are kind of small terrestrial planets. Much farther away from the sun, we've got our gas giants, so Jupiter, Saturn, Uranus, Neptune, sort of on the outskirts of our solar system. And other than that, we know that we have a few different sort of belts of debris. So we've got the asteroid belt that's between the inner planets and the outer planets. And we've got a few other small bodies kind of floating around in here. But looking at this model of the solar system, there's one really important observation that we can make right off the bat, which is that looking at this picture, we can tell that all of the planets are basically in one single plane. This orbit that's not in the plane is Pluto, but for our purposes, we're not gonna worry about Pluto. So all the planets that are planets are in our same plane, and they're all moving in about the same direction. And I realize that sounds like a really kind of obvious thing to say, but it's actually a really important observation. And it's something that tells us sort of exactly where the solar system had to get started. And the reason it does this is that in astronomy, a lot of the time, if you see a disk, we know that that disk had to start as a big sort of cloud of dust that then collapsed under gravity and eventually formed this disk. So for the case of our solar system, we know that our solar system needed to start as a big kind of diffuse cloud of gas and dust. We call this the nebula, and then it eventually collapsed down into this disk. So because we start with a nebula, we call this the nebular hypothesis. It's an idea that's been around for quite a long time, actually. Laplace sort of wrote some of this up back in 1796. But the picture, the general idea has remained the same. So to look at it a little bit more closely, if we start with our nebula, so these are usually just a lot of hydrogen and helium. So if we start with our big hydrogen and helium cloud, and we let gravity do its thing for quite a while, gravity will start to pull the particles of that cloud closer and closer together. So it'll start to condense. And there's an interesting thing that will happen here, which is that if our cloud has a little bit of spin in this picture, it's spinning a little bit counterclockwise. Because of this particular idea, which we call conservation of momentum, what conservation of momentum tells us is that as this cloud is collapsing, that spin that it has initially is just going to be exaggerated more and more as it collapses. So early on, it'll be a big diffuse cloud, not spinning too much. But by the time it's really starting to condense, it's going to be a much denser cloud, and it's going to be spinning much more quickly. And the other thing we know about things that spin in space is that if a cloud is spinning, it's going to start to get flat. And it'll start to get flattened into a disk shape. And so as this happens, our collapsing and our spinning and our disk shaping, what we'll end up with is this sort of center area where our star will sit. And then this big kind of disk of material around that we're eventually going to make into our planets and other objects. So this is the general idea of how these planetary systems are first getting started. And so one of the questions we might have is, with this starting nebula, exactly how much stuff do we actually need in our starting nebula? So we'll talk about that in a second. I got ahead of myself, actually. So the one kind of cool thing is that we can check this idea by just looking around in our galaxy and seeing if we actually see any of these clouds. And the great thing is that we do. So a couple examples on here. On the left is Barnard 68. So you can see the kind of rough outline of the dark cloud here. Um, this is a relatively close cloud, about 500 light years away or so. Um, but there are also many other examples. So on the right is, for example, the Orion Nebula. So the Orion Nebula is in the background here. And then if you were to zoom in on some of these tiny, tiny specks within the Orion Nebula, we would be able to start to see that some of the gas and dust has started to make these various features. So some of them look a little bit like collapsing clouds, some of them look a little bit disky already. And so in seeing these images, we can start to confirm that going from a cloud to some sort of disk-like structure is a pretty reasonable thing to happen. Okay. But I mentioned that we wanted to figure out how much gas and dust we need in these clouds. And to do that, we can do a kind of cool trick. And the thing that we're going to start with is the assumption that this original big cloud of gas and dust probably looked pretty similar to what ended up being in the sun. And that's great. We know quite a bit about the composition of the sun. So on here, we know that it's mostly made of hydrogen, this big red slice. We know that there's kind of a dollop of helium in there, and then there's this tiny, tiny sprinkling of other elements, so oxygen, carbon, and so on, that are also in our sun. And so we can make the guess that our original cloud of gas and dust would look something like this, mostly hydrogen and helium, and a little bit of everything else. And in our original cloud of gas and dust, the way that we can kind of roughly picture how this gets separated up is that we can think of the hydrogen of helium as mostly making up the gas, and then everything else being the components of dust. So this is what we're sort of aiming for composition-wise with our original cloud. And what we might notice is that the planets really don't look like this today at all. So if we take a look at the composition of our planets, the terrestrial planets here on the left are definitely, they have a lot of rock. The gas giants might have less rock. They have gas, as their name would suggest, but they're definitely still not at that nebula stage of having mostly hydrogen and helium gas. And so what we need to do is to figure out how much of that initial gas and dust we need in order to kind of boil it all down to this particular amounts of rock and waters on here and various other materials in order to make our planets. And so the calculation that people have done is basically to sum up all of the mass in the planets. So we add up Mercury and Venus and Earth and so on. We figure out what these planets are made of. And then taking the mass of the planets, we're going to just supplement their masses. We're going to add on a bunch of hydrogen and helium gas until we build all of that stuff up to the composition of the sun. And by extension to the composition of our initial nebula. So a number of people have done this. If you go through this and you sum up all your planets and then you scale it all up to match the composition of the sun, what you find out is that you actually only need about 1/100th of the sun's mass in gas and dust to make our planets. So it's really not too crazy, actually. So if we've got all of that set, we've got enough mass for our sun, we've got enough mass to put into these planets, then we can safely go from this diffuse cloud condensing down into a disk where our planets will come from. So if we've got a disk, the next thing we want to do is we want to take all of the kind of random dust and gas in that disk and we want to squish it into our planets. So that's our next step of going from this kind of disorganized disk into a set of planets. And it's at this stage that we reach that protoplanetary disk that I mentioned. So we've got our star in the center, and then we've just got this big kind of mess of gas and dust around our star that we know needs to condense into planets, but hasn't quite reached that stage yet. So in this protoplanetary disk is where we're going to grow our planets. And when we talk about growing planets, we usually describe that happening in 3 different stages or 3 different categories. So naturally, we're going to start with the smallest thing. We're going to start with dust. Space dust tends to be about a micrometer in size. So you could just kind of picture dust around your house. And like the dust that you find around your house, dust tends to sort of stick together and coalesce and form dust bunnies. And so if we've got our dust forming into dust bunnies, we could imagine if we squish a bunch of those dust bunnies together, we can start getting larger and larger objects. Um, and if we do that a lot, we could get all the way up to the size of something that's maybe about as big as an asteroid. So maybe up to kilometers in size. And when we get to that point where we have a pretty sort of well-defined object, that's what we start to call planetesimals. So we have our dust that's tiny, tiny grains. We've got our planetesimals that are sort of more larger defined rocks. And then what we can do as a final step is take all our planetesimals, start squishing those together through gravity. And eventually we should get to a point where we've got enough planetesimals that we can start making sort of the solid rocky cores of our planets. You can imagine these solid cores looking something like Mercury or Mars, where it's just really just kind of like a big spherical rock. And that'll be sort of the last stage of this solid growth. So dust, planetesimals, and then solid cores is where we're going. So we have these three categories, and there was actually a really interesting problem that people had for quite a while, which was that that first step of going from dust to planetesimals is actually quite difficult. It turned out when people were looking at these protoplanetary disks and then thinking about how you grow various objects, as soon as you hit about a meter in size, those objects tended to either break apart really quickly or drift right into the sun. And that's obviously a problem because if you want to make planets, you can't just lose all your material by throwing it into the sun or breaking it apart into a million pieces as soon as it forms. So people called this the meter barrier because we couldn't get past a meter. And quite a bit of work has been done on this over the years. The general solution that people have come to is that we can overcome this meter barrier if we really pay close attention to what's happening in these protoplanetary disks. So I just kind of put an example of a cross section of a disk on here. It's not too important exactly what's going on, but we know that we've got a star in the center. Our star is outputting a lot of energy. In the disk itself, things are pretty chaotic. There's grains sort of mixing around. There's energy coming in from the star, from other sources. There's energy going out as the disk is cooling. So there's all kinds of stuff going on in these protoplanetary disks. And the thought is that if we take all this into account, all of the mixing and everything, we can sort of keep these meter-sized objects in place long enough to get them past that meter barrier and get them forming larger objects. So that was good news, that if we pay more attention to our disks, we should be able to get past that issue of the meter barrier. So if we get over our meter barrier, the next kind of thing that we need to contend with is that if we go back to our first clue and we look at the structure of our solar system, as we mentioned, we've got all these small rocky bodies close to the sun, and then we've got all these really giant objects farther away. So that was the next issue people were thinking about. How do we make sure that the objects that are farther away are more massive and have a lot of gas, whereas the ones towards the center are much smaller and just have rock? And this problem helped us understand an important kind of feature of solar systems, which is the ice line. Sometimes it's also called the snow line or the frost line, whatever cold term you would like, that line. The ice line, though, is basically just showing where it's cold enough to have ice, kind of as the name suggests. I generally think of this sort of like if you look at the mountains, right? There's a line where above you can have all the snow and below it's all going to melt. The ice line is basically the same. So it's a point in our solar system where beyond the ice line, we're going to be far enough away from the star that we can hold on to ice. So things will be solid and frozen. But if we're within the ice line, we're going to be too close to the star. And so material is going to melt or it's going to turn into gas and evaporate. So our particular ice line in our solar system is somewhere sort of between Mars and Jupiter, which you might notice sort of perfectly splits up our planets into the rocky ones inside the ice line and the giant ones outside. And so our thought here is that if you're outside of the ice line and you've got all of these ices, ices are really useful because they can help sort of start building up these solid cores much more quickly. So if you're outside of the ice line and you can build up your cores super quickly with ice, you can start to get giant planets more quickly on the outside, whereas on the inside, you don't get that extra boost from these ices. So our difference between giant and tiny planets led us to some knowledge about the ice line, which is useful in making this distinction between the two types. Okay, so far what we've done is we've taken our cloud, we turned it into a disk. Within that disk, we started building up some dust, and then we started building up some planet cores. And so one of the questions we might have now is just like, can we actually see this process happening? Can we see these planet cores anywhere in disks? And the answer is yes, so that's great. So we were able to actually image a number of protoplanetary disks and kind of check out and see what their disks are doing during the star's lifetime. So this was a project a few years ago. A bunch of astronomers were working with ALMA, so this radio telescope in the Atacama Desert. It's actually many, many kind of tiny telescopes all working together. So this is sort of a from above view of all of their dishes. But because they had a radio telescope, they were able to take radio images of these stars that they thought had disks around them. And what they found was something like this. So they imaged all these stars. They were able to pick up their disks. And so in all of these images, the star would kind of be towards the center of each one of these disk shapes. And then the colors in these images are showing you where the dust is. So that's what's really valuable about the ALMA telescope actually, is that because it's in the millimeter, submillimeter, it's going to allow us to pick up and see where dust is, which is great because we want to start seeing where our dust is moving when planets are showing up. And everyone was super excited about these images because, as you can see, we can see a ton of features in these disks. We can see places where there's a lot of dust building up, where these colors are brighter. We see lots of rings. We see gaps where the dust has kind of cleared out. And everyone was really excited about this because we think it's a good sign that some sort of planet formation is happening right now, right? So we're somehow getting our dust into different formations. One of the thoughts was that these kind of big empty rings were where a lot of the dust had already been collected into a solid body, and so it had just sort of cleaned out the entire ring around the star. So this was good evidence that at least something is happening early on with these disks around stars, and that the dust is in motion and starting to organize itself. Okay, so if we've convinced ourselves that we're able to take the dust and we're putting it in solid cores, the next thing that we really need to contend with is the gas that's in our disk. We had gas and dust, we took care of the dust, we now need to figure out where the gas goes. And living on Earth, we kind of know where we do want the gas to go, which is into our atmospheres. The atmosphere on Earth is super important for us. Gases in atmospheres are also really useful for the giant planets, the gas planets as well. And so we need to be able to get our gas from our disk and stuck onto our planets. And this process is actually relatively straightforward. So as we're building up to larger and larger sizes of objects, once the objects are large enough, they're going to have a pretty good amount of gravity. And so they can start to just sort of hold on to and sweep up the gas that's near them as they orbit around their star. So you can see that in the third panel here. We've got our planet or early planet moving through the disk, and it's just going to start sweeping in these long arms of gas and adding that gas to its atmosphere. So a note about these atmospheres is that, as we mentioned, the nebula is mostly made of hydrogen and helium. So that's the material that's available to us. So when these large planets are sweeping up gas, they're going to be sweeping up hydrogen and helium. So they're not going to look like Earth's atmosphere today. And for that reason, we're going to call these atmospheres primordial atmospheres. So they're sort of our first go at atmospheres. Some planets might have a second go. We'll see that in a second. But our primordial atmospheres are those really kind of thick hydrogen and helium ones that you get on the early planets. And just to show the difference, so these are roughly the composition of the atmospheres for the different planets in our solar system. Um, the terrestrial planets are on the top half, our gas giants are on the bottom. And what you might notice is that the gas giants, so Jupiter, Saturn, Uranus, Neptune, all have really large amounts of hydrogen, a good chunk of helium, and then some other stuff added to them. And this is great because that pretty well matches the gas that we think would have been floating around in the solar system really early on when these planets were first forming. So they just held on to that hydrogen and helium from the nebula and kept it around. So our bottom four have these primordial atmospheres, but our top four look quite different. Earth's got a lot of nitrogen, Venus and Mars have all this carbon dioxide. And so what that tells us is that our inner four planets, maybe they had primordial atmospheres to begin with, but they were able to get rid of those atmospheres. And instead they have these secondary atmospheres. So thinner atmospheres, you usually get these through processes on the planet's surface, like volcanoes. If something comes and collides with the planet, it can, leave behind a lot of gas that can go in the atmosphere as well. So our inner four planets got rid of those primordial atmospheres and now have their secondary ones. So as we're thinking about atmospheres, we can just remember that the first set that we get that we really work with is the primordial ones, and the secondary will come later when we think about each planet sort of individually. So this question of atmospheres actually tells us another really important detail about planet formation, which is that it's going to give us the cooking time for a planet. It's going to tell us how long we have to get these planets assembled. Because we know that our gas planets are going to be able to grow and grab onto gas until the disk runs out of gas. And so what we can do is we can look at lots and lots of different stars. We can see whether or not they have gas disks, and based on the ages of these stars and whether they or not they have disks, we can figure out how long these disks actually stick around. So a number of people have done this. This is one example of what people generally find. So on this plot, all of the black circles are different stars. On the horizontal axis is just how old the star is. And then on the vertical axis is how much gas they have. So towards the top, they've got their whole gas disk. So we're just kind of starting out. And then at the bottom, they've gotten rid of all of that gas. And what people find is that after about a few million years, so maybe 5 to 8-ish million years on here, most stars will not have a gas disk anymore. And that's really useful because that tells us that our gas planets like Jupiter or Saturn, they need to be done in a few million years. They need to be completely assembled because after that, the material is gone. And that's really quite quick, a few million years. It doesn't sound like it, but in space, that's like a snap of your fingers. So we need to get these gas giants going really, really fast. And naturally, if we're able to make their cores grow fast with ices, that'll help with this process. All right. So far, we've got our cloud of gas into a disk. We condensed our dust into solid cores. We thought about the ice line a little bit and how that helps with these planet cores. And then we figured out that within about 5 million years, the larger ones need to sweep up a bunch of atmosphere. So that's our general picture at this point. And what we'd like to do with it is just to check it against exoplanets. So we've mostly looked at the solar system so far, but we want to know, right, does this also explain exoplanets? Because if it doesn't, then we might have a problem there. So we're going to look at a bunch of different exoplanets and see how they all measure up. This is just, as it's titled, the latest data from NASA's Exoplanet Archive, pulled off a couple days ago. On the right is their newest discovery. Can't say much more about it than what's listed there. But on the left here is their running count of the number of confirmed exoplanets. So we're pretty good at finding these at this point. We know of about 4,000 of them. And as you can see from this little graph, most of those planets that we found are a good deal larger than our terrestrial planets. So these are pretty large, up to Neptune sizes or more. So we want to use these 4,000 planets to see what we can learn about planet formation. And to do that, we need to figure out what we can actually learn from these exoplanets. And what we learn about an exoplanet really depends on how we find it. So there are lots and lots of different ways of finding exoplanets. Um, I'm really just going to focus on this first method, the transit method. And the reason I want to focus on this one today is that it's going to tell us about the radius of the planet. And that's information that's proven to be really, really helpful in planet formation. Um, so this transit method, the other reason it's kind of good to talk about is that it's responsible for most of the planets that we've seen. So this is just kind of a quick rundown of how many of the exoplanets we know of are discovered by each method. Transits are responsible for about 76% of them. So it's a pretty efficient and effective method of finding planets. Okay, but how does it work? So the way that we can find a planet through transits is that we'll plop down our telescope. We'll look at a star that we think might have a planet going around it. And what we want to do is just measure the brightness of that star. So if there's no planet in front of the star, it's just going to be kind of normal full star brightness. But if we wait until the planet crosses in front of the star, then that planet is going to block a little bit of the star's light. And if it blocks the star's light, we should be able to measure that. We should be able to see that the star is getting a little bit dimmer. And if it gets a little bit dimmer, then we know that there must have been an exoplanet there. And the other really important thing about this is that, let me pause this, pause it at the right moment. There we go. Is that the amount of light that a planet can block is just going to depend on how big it is. So if this planet were bigger, it might block more light. If it were smaller, it would block less. And so that tells us that if we look at the brightness of the star during a transit, we can figure out how big the planet is. And as I mentioned, that's the thing that we really want to know. So the other nice thing about transits is that they're sort of ongoing right now as the focus of space telescopes. Y'all might have heard of these, but Kepler was working on finding planets through the transit system for years and years and years. It found most of those 4,000 that we mentioned. More recently, TESS has come online, and TESS is doing same job with a new batch of planets. So there are new planets coming out almost literally every day. So it's a fun field to be working in right now. Okay. So I mentioned that we're interested in radius of planets. And the reason for this is that we just want to know, like, what kinds of planets do we need to be making in this planet formation process? And so once we found a good number of planets through the transit system, astronomers started plotting out what sizes they were. And they came up with a plot something like this. So this is relative to Earth. How many planets do we have at these particular sizes? And as you can see here, there was an interesting pattern where we found a lot of planets about 1.5 Earth radii, a lot of planets around 2.5 Earth radii, and really not all that many in between. So we've got this gap here, and so people called it the radius valley in exoplanets. And the radius valley is kind of an ongoing question. There are a few different ways that we can start to explain this. And the kind of leading way that I'll share with you today has to do with atmospheres. But to discuss these, I just want to introduce one little bit of terminology, which is that we named these two peaks of planets. So the first peak was just a little bit bigger than Earth, so we named it super Earths. The second peak was a little bit smaller than Neptune, so we named them sub-Neptunes. It's not terribly creative, but it helps us keep track of these planets. So in our planet formation process, we need to figure out how do we make super Earths and sub-Neptunes and not really anything in between. And as I mentioned, atmosphere is really the thing that solves this problem. So what we can picture is we've got our disk. We made some cores. Our solid cores have picked up a bunch of gas. And if your core picks up a lot of gas, it's going to get pretty puffy. And so we can imagine that if you've got a planetary core with a lot of gas, it's going to look like a really puffy planet. And so if we were to look for it in a transit, it would look like a pretty enormous planet. And so that would put it in the range of our sub-Neptunes. But now you could think, if we take the sub-Neptune and we somehow get rid of a bunch of its atmosphere, now it's just a little core and a very, very thin or no layer of atmosphere around it. So now if we were to look at this planet, even though it has the same core and it sort of started out the same way, in our transit, it would look a whole lot smaller. And so in this case, if we're able to get rid of all that atmosphere, make our planet look a whole lot smaller, we would be able to get to the super Earths. So between sub-Neptunes and super Earths, the name of the game is always getting rid of that atmosphere and making the transition from having a puffy sub-Neptune down to having a super Earth planet. And I'll just mention there are a lot of ways actually to lose atmosphere. This is something that people are actively working on at the moment, but some options are that, you know, stars are really hot, they're outputting a lot of energy, that can help get rid of some atmosphere. Another thing that can help is that planets, as soon as they form, tend to be really hot, but if they cool down and they push a lot of heat away from them, that can also help get rid of atmosphere. So there are a lot of options, and this is something that's kind of ongoing, how we get from these super Neptunes, the sub-Neptunes to super Earths, how often these processes happen, if they happen always, and all those kinds of fun questions. So anyway, once we add in our exoplanet observations, we've now covered the solar system planets, our gas giants and our rocky ones. We were able to explain some of the features in protoplanetary disks. We explained the radius gap in our exoplanet observations. And so to finish everything off, what I'd like to do is just zoom in on the Earth and think about kind of the finishing touches that need to happen in planet formation. The Earth has so many things going on its surface, but I'm going to kind of handpick 3 things that we'll talk about. And those three things are cratering. So we see a lot of cratering on Earth, both big and small. We see it on the moon as well, which we need to be able to create the moon around the Earth. So that's our second project. And then finally, one of the main kind of features of the Earth is that we've got all of this water and oceans. And so we want to figure out like how that got here as well. And potentially other materials as well. So those are our 3 things to focus on: cratering, moons, and water. And the reason I sort of picked these 3 topics is that they can all be explained by a similar process. And that process is just through collisions. So collisions between our planet and whatever kind of rocky objects are in our solar system. We know that there was a lot of just stuff in our solar system right after the planets formed, because when you form planets, you can have a lot of debris left over. So things that were starting to grow but didn't quite make it up to planet size. Any of these things are like fair game for coming and colliding with your planet and causing all kinds of interesting reactions after that. The other kind of cool thing about collisions is that they're ongoing. So we're like experiencing them now. On the back here is just a map of all of the meteorite events, or most of the meteorite events at least, from 1988 up to last year. And so these are happening fairly frequently. As you can see, a lot of them aren't too energetic or anything, but there are a few that can get pretty exciting. One example is a few years ago, the Chelyabinsk meteor or fireball. That was a big event. So we know that these types of collisions are ongoing, even if today they're on a much smaller scale. So you can imagine way back when we had things like the size of the moon or Mars kind of zooming around the solar system, these types of collisions would have caused way more havoc and excitement. So we have our collisions. And as I mentioned, we want to apply these to the moon formation and then to water on Earth. So we'll go ahead and do that. The moon formation is really cool work. A lot of it's been done at UC Davis, actually, in California. The theory is that if you take an early Earth and you imagine that there's some object, maybe about the size of Mars, that comes by and just slams into the Earth, kicks up a ton of debris and rock, what could happen is that when we have all that debris around the Earth, it can very slowly sort of start recoalescing into a body. And if that happens, we can get our moon kind of nice and compact next to the Earth. So in this sense, collisions can help us explain things like the moon. And as I mentioned, collisions are also a really good way to add anything you'd like to your planet. Specifically, they're great for water. They could also deliver any kind of other special material that we need on our Earth. But water is one of the big questions, so I'll focus on that one here. And to think of collisions as a water delivery service, what we want to go back to is that picture of the solar system with the snow line. So inside the snow line, right, it's really hot. So any water that you have is probably just going to evaporate into gas. But beyond the snow line, you could definitely have water that's still liquid, or water that's frozen in ice in various bodies. And so what you could imagine is that if we form our early Earth somewhere in here, somewhere close to our star, and if we wait long enough for some of the rocky bodies from out here beyond the snow line that have all these ices coming with them, if we wait for those bodies to make their way into the solar system and collide with the Earth, that could be a really good way of bringing some of this water onto the surface and making that available for oceans and whatnot on Earth. So this is another kind of finishing touch that you can add to your planet once you've got it all assembled. So I'll stop there with our details on planet formation and just leave up some takeaways. So we know a lot about planet formation, both from within our solar system and from far, far away from our solar system. We can use all kinds of different data to learn about planets. So images, we could take samples, we can do experiments in the lab to figure out what's going on with these planets. And then we talked about the 4 clues and what those can tell us. So we know that our own solar system structure can tell us about gas collapsing. Our protoplanetary disk images can tell us how things are growing and when they're growing. If we look at exoplanets, we can learn about how atmosphere will impact the final features of the planet. And if we look really carefully at the Earth, we can figure out how these kind of final collisions and dynamics with things in our own solar system were able to add some extra special features to our Earth's surface. All right, so I'll end there and take questions if there are any.
So please feel free to unmute and ask a question.
Isabel, I'm Pete. You started off early on, you started off talking about this giant cloud of gas and dust that eventually became a disk. What I didn't understand is, was the sun already created at that point, or did the sun come out of that same original cloud?
Oh, that's a question. A good question. Yeah. So the sun would have come out of that same big. Oh, here's a picture. That same big cloud of gas and dust. So at the very center is sort of where stuff can get compacted the most. So towards the center of this cloud is kind of where you would expect a lot of that material to get super compacted together and eventually get hot enough that it can start burning some of that hydrogen that it has, sort of, and that would kickstart it into that phase of being a star. Yeah, so we get our star in the middle, you can imagine, of this cloud, and the rest is going to kind of flatten down into that pancake of a disk.
Thank you.
Yeah.
Isabella, this is George. You mentioned about the moon, the formation of the moon with the impact of the Mars-sized object. Do we think that all the other moons and the other planets were formed similarly, or did they just coalesce around the disk of the planet?
Yeah. So I believe most other moons, you can usually make them through just coalescing at a similar way. So your planet might have a disk, and then that can coalesce into planets. Our moon is a little bit unusual in the solar system just because of its size relative to Earth. And so for that reason, people have kind of figured out that you need a different mechanism to make our particular moon. Yeah, so it was made necessary by our moon, but it's definitely not a process that needs to be unique to our planet. It could certainly happen elsewhere, though it's unclear if it really did or not.
We have a question in the chat. Why do spinning disks of gas and dust flatten?
Yeah, so it's something that will happen to almost anything that spins. You can imagine, pizza dough actually does a similar thing, right? You spin it around and it kind of spreads out and it gets flatter. And it's also, if you spin like a bucket of water or something, it'll kind of press out to the sides. So this flattening is something that's kind of inherently associated with something that's spinning rather quickly. Yeah, it's the same reason that we can use spinning to create mirrors for telescopes, because it's really great at sort of flattening things out and spreading it all out. So yeah, so spinning is very, very useful, both in space and not in space.
Also, the Earth, it's kind of flattened because of the spinning, you know, on the
Yeah,
poles.
definitely. Yeah, so that'll help us as well, get that kind of egg shape. Yeah.
Isabella, this is Steve. Am I on?
Mhm.
And I remember when the first exoplanets were discovered, they found some gas giants very close to the sun. There were Jupiter-sized planets near Venus. And I may have misunderstood what you had said earlier, that we thought that, or that I thought you were saying the same thing, that we would find planets like they are in our solar system with the solid planets in and then the gas planets out.
Yeah, so you're actually hitting at something that's a pretty big debate currently, which is, when you find a gas giant close to the star, did it form there or did it migrate there? So did it form elsewhere and eventually make its way in? And there's a lot of support for both sides, and it's very possible that both happen, that sometimes giant planets form kind of beyond the snow line where we might expect them to, and then they migrate in. And it's possible that there are ways to form these gas giants much closer to the sun. One of the things that a lot of people think about is, in this process of having a disk of gas, when people simulate that, you can sometimes make gas giants sort of directly out of the gas. So you add like a little bit of an eddy, and then all of your gas can get piled up and start to form into a planet. So both are options, and it's unclear exactly when one or the other might happen. And it's also unclear if we can really tell, when we find a gas giant, if it formed there or not. Currently, that's a little bit hidden, but there may be ways of figuring that out in the future.
Thank you.
This is Kent. Wouldn't there be some centrifugal force associated with the spinning disk that would cause it to expand and flatten?
Yeah, so we do get a lot of that early, right? So we're going from it. Where did I have that? Let's see. So we do find or expect that our disks are getting flatter and flatter as time goes by. Yeah, so you're definitely right there. And it's because of that we're able to sort of start making these disk shapes outright. But if we think about the material in this disk, I think we can generally make our planets fairly quickly, so that by the time that things are spreading out and kind of everything is becoming much more diffuse within the disk, we can already have our planets kind of set and going in there. And we can have a little bit of help keeping it together through gravity and other things as well. So it's, yeah. But you're right, these disks can sort of change in size as they're evolving.
Oh, I have a quick question. I was looking at, how do you guys differentiate between planets with sort of large rocky cores and thin atmospheres, and small rocky cores and large atmospheres? Are you guys using like spectra, or like, so how do you tell the difference between those two?
Yeah, so to do that, usually what you need to do is you need to get observations multiple ways. So there we go. So, so the transit method tells us the size of the planet, but if you were able to get a radial velocity detection, for example, radial velocity will tell us something about the mass. And so usually the way it goes is that if you have a pretty small mass but a really big radius, you know that you're looking at a planet that's mostly like puffed up because of gas. Whereas if you had a larger mass and the same radius, you would have much more rock in there. And then naturally, if you've got a large mass and a very small radius relatively, you know that you must have very little atmosphere on that planet. So yeah, so to pick out the specifics of that, definitely we need to do, we need to get observations in multiple ways. And radial velocity is definitely the second best contender on here. So radial velocity takes a little bit more time because we need to study the spectrum of a star, but it does give really great information about masses. And that's something that, as you said, we definitely want to know that.
Thank you.
Mhm.
A question. Does the angular momentum of the galaxy have anything to do with angular momentum of these gas clouds?
Yeah.
Is that why it's starting to spin up?
That's a really good question. And I think possible like relations between the galactic environment and solar system is like, that's a really interesting question. I don't think a lot of people work on it. So you're very forward thinking in that sense. But as far as the gas clouds, as far as their condensing, I think because gravity kind of, you know, gravity will work best sort of locally. So it's really the gravity and the mass of the cloud that'll determine whether or not it condenses, although it is being sort of, you know, spun along in its orbit by the rest of the galaxy. But as far as the collapse, I think the physics that we usually think about is just the gas cloud itself.
How in the original disk, before the planets were formed,
Mhm.
was how was was there some kind of clumping that took place that eventually led to planets? Or if you had just a consistent disk, how does it form into separate bodies?
Yeah, good question. So we always need some kind of like seed to get started with building something. Um, so a lot of the times it could be you've got a disk, but in one part of the disk, it's like ever so slightly more dense than the other parts of the disk. And if that's the case, then that part is going to start just condensing under gravity and working the same way as our disk actually. It's going to start condensing, it's going to start forming a solid core there. So that's one option, that you might just have a little bit more material in one part of the disk than another. And that'll just happen because our disks aren't perfect. Our starting clouds aren't perfectly spherical or anything like that. So we can get a seed to start a planet that way. The other option is kind of what I mentioned with the gas. Like if you've got, you know, the gas probably won't flow around perfectly. So if you've got just like a little bit of an eddy or something in your gas, that can also sort of kickstart a place where material might start coalescing and grouping up. That was another interesting thing that came about with those ALMA disks, is that people were starting to see that, oh, we can carve out these really big gaps in the disk, and that can also help us start to shepherd material into particular places in the disk. And if we've got our material sort of separated out like that, it's going to be way easier for it to start to come together in planets. So yeah, so any kind of irregularity in the disk is going to help push this process along of starting to make bodies that are bigger and bigger and bigger until they become planets, or eventually kind of lead up to planets.
So why are the rocky ones closer to the sun and the gas ones further away?
So part of the thought there is that when we make small planets close to the sun, they might hold on to some gas originally. So they might have one of those primordial atmospheres. But because they're really close to the sun and they're pretty hot because they're close to the sun, it's going to be really easy to make that atmosphere escape. So you can heat up all the particles in the atmosphere, and because they're moving so fast, it's possible that a lot of them are just going to be able to escape the planet altogether. So if that's the case, then if you had rocky planets with an atmosphere and you blew all of the atmosphere away, then what you're left with is just the rocky planet. And then you can go about forming your secondary atmosphere or whatever else needs to happen on that planet. But yeah, so the reason would be that you did have an atmosphere and you got rid of it just because you're close to the sun and it's a really high temperature. And so you can excite the gas and kind of make it disperse.
And do the gas ones have rocky cores?
Yeah, that's actually another point that we're uncertain about. We think the ones in our solar system certainly do, but they don't necessarily need to. To figure that out in our solar system, you can kind of do some fancy measuring of the gravity around a planet, and then you can figure out how dense it needs to be at different parts. For exoplanets, it's obviously a little bit harder. The best you can really do is measure your mass and your radius and figure out if that on average gives you something that's mostly gas or that has a lot of rock in it. So we kind of assume that the gas planets have some sort of core, but it's a little bit unclear.
Well, to that point, if all the planets were formed from dust coalesced together to form a kilometer asteroid, so that means probably all the planets probably have some rock in the center of it.
Yeah, so that's the reason that if they have cores, that fits kind of nicely. There are kind of groups of astronomers who think that because you can make a planet by like creating a little eddy in gas instead, we might be able to kind of bypass the cores. It's sort of up to debate. Unclear. Yeah, naturally there are the debates about how exactly you can make a planet, and I think generally like it's very likely that all of these different processes are at work, right? And we just, in our solar system, one thing happened. In another solar system, perhaps the conditions were set up so that a slightly different process took over. And so the game is just kind of figuring out exactly when each thing might happen and why.
Quick question. Has there been a sort of survey of the composition of nebula, or so you talk about the sort of like gas, at least composition of these disk clouds?
Yeah.
Are those similar across the board, or is there sort of like variations in composition of those gases?
Yeah, that's a really good question. I believe generally they're fairly similar. The exception may be in like particularly crazy places in our galaxy, like the galactic center. I don't know of the data or the numbers or anything, but I would say like if there were an exception, it would probably be there. The clouds will vary a little bit, so they'll all be mostly hydrogen and helium because that's mostly what we've got. But the part with the other elements could change a little bit because we're just getting those elements from the remnants of past stars. So if a star reaches the end of its life, it's going to explode, feed all of its material back into the local region, and then that can start going into these clouds and starting the process over again. So you could expect a little bit of variation just sort of by chance of what material you happen to scoop up and from what stars and what the compositions of those stars were. So it's it feeds back into itself a little bit.
So I have a question. So you talked about the water on Earth.
Mm-hmm.
Now, is that a theory? And if it is, are there other theories as well?
About other ways to get it here?
Yeah, you said it came from by collisions from other external bodies.
Yeah, I would say that's probably the favored theory. Mostly because collisions are the kind of most common thing that you'd expect to happen after forming your planet. Um, I think there are also people trying to figure out, because it's a little bit unclear, if you could just form the Earth in place with enough water. Um, I'm not sure there's a conclusion on that. So if it needs to be delivered afterwards, I think something like a comet or an asteroid is probably the best bet, though there are debates about whether it should be a comet or an asteroid or something bigger. And so that exactly how that delivery might happen is a little bit unclear, but it does seem really likely that it would come through a collision with some sort of other object in our solar system.
But you still have the question of how the water formed on those bodies. So, how do you get from this hydrogen
Yeah.
dust to water? And whether it formed here or on those other bodies, it still had to be formed.
Yeah, so water can be formed and exist in your original disk. And it just so happens that if you've got water in that disk outside of a particular radius, you probably expect it to kind of stay either solid or liquid. Whereas where the Earth is currently, we kind of expect that the water shouldn't have been able to stick around as a liquid or solid that could be added to the planet. The Earth is pretty close to the sun, so we think it would be a little bit too hot for that to happen. And so if that was in fact the case, then we would need one of those objects that are farther out that formed with water and was actually able to hold on to that water to come and deliver it later on. Yeah, but water is one of the things that could come with us in that original diffuse cloud and then down into a disk.
Other questions?
Quick, sorry. I'm Nathaniel Bates. I appreciated can you hear me?
Yeah.
I appreciated your presentation. Thank you. Maybe possibly talk about, okay, here's the one for the crazy people. It's nighttime, panspermia, and theories about panspermia. You mentioned water coming to Earth. Do you think that there's possible evidence for some type of complex organic compounds that maybe could seed some of these early solar systems? Or is this just late night talk radio stuff? What's your opinion about that? My answer muted. Thank you.
I think the interesting thing about these collisions is that you could argue that almost anything was stuck to one of these asteroids or bodies that came and hit the Earth. I don't think I can really make any claims about, exactly what those things were, how complex they were. But I mean, certainly some people have suggested that, some of the essentials for life might have come on some of these collisions. So in that sense, maybe this helps kickstart things. I think when you start talking about life, it's always really difficult because we're still learning so much about the planets themselves that you can do so many like small tweaks to your planet formation theory so that it could fit almost anything. But I think learning more will help kind of narrow down those types of questions and theories and figuring out exactly what are the reasonable ways to get life onto our planet. The other reason it's really difficult is because we've got like this one sample, right? We've only got Earth. Maybe we have phosphate on Venus, that's a whole other can of worms. But for now, our only real example is life on Earth. And so because of that, there's just so many different ways that you can get to having life on Earth that it's really hard to narrow it down or really say anything super concrete. I hope that answers your question.
Any other questions? Going once. Well, I want to thank you, Isabella. That was a very interesting talk. The link to this recording will be sent out. And you can always find it on YouTube as well. I forgot to mention that on December 9th, there will be a webinar put on by MDIA, the Interpretive Association, where I will be putting together a short talk about astronomy on Mount Diablo with a bunch of great images from our imaging group. So if you can join that, I'll try and find a link to that and send that out as well. So it'll be December 9th, a Wednesday. With that, everyone have a excellent holiday season. Be safe, stay home, wear a mask. And we'll see you all in 2021. Thank you.
Thank you, everyone.
I enjoyed it. Thank you. Thank you very much.
much.
Thanks for being our president.
Thank you, Steve. Been a good run so far. Now we'll
You've
change
done a
hands.
great job.